see. My name is Jeremy Gregory, and I'm a research scientist at MIT and the executive director of the Concrete Sustainability Hub. And I'm going to be talking to you today about some of our research related to albedo, climate, and urban heat islands. And this work was done by a whole team of people, Jin Zhu, Li Yizhu, Adam Schlosser, and MIT. And as you'll see, we had some people with diverse backgrounds because this is a complicated question. But what I want to start out with is talk a little bit about, basically unpack what each of those terms means in the title there, starting with albedo. And basically this is something we just get from physics. It's pretty simple. It's albedo is a measurement of the fraction of solar radiation that's reflected from a surface. And generally we talk about it on a scale of 0 to 1 or even percentages. And a high albedo surface will reflect a lot of radiation from the sun, whereas a low albedo surface doesn't reflect much. And of course, whatever isn't reflected is absorbed by the surface. And our planet, as you can imagine, has a whole bunch of different surfaces with different albedos. You know, snow has a high albedo, whereas many urban surfaces have a low albedo. On average, though, the Earth's albedo is about 0.3 when we look across everything, and it turns out that's about the color of grass. So we must have a lot of, obviously we have a lot of green and blue on our planet. But next I want to move on to climate, and what's interesting about climate is that it's actually affected by albedo. And so albedo is something that has been studied for many years by climate scientists, because there's essentially three main factors that affect the climate of our planet. You know, one is how much solar energy is coming in, and then two has to do with the chemistry of the atmosphere. And of course we need that chemistry in order to trap in some of the heat that we receive from the sun, and so that having that proper balance is really important for creating that greenhouse effect to keep us warm. And albedo is actually the third factor that has a big impact on how much of that solar energy is absorbed or radiated back. And so climate scientists have been looking at all kinds of things, such as what's the impact of aerosols in the air, and volcanoes, and of course emissions, other anthropogenic emissions as well. But what they're also interested in is what's the albedo of the surface, and they've been studying topics like what are impacts of deforestation, what's the impacts of losing glaciers and snow, and how does that affect our whole climate balance. So like I said, this is very much a topic that's been of interest to climate scientists. The last term that I had on that title was urban heat islands. And basically an urban heat island just means that the temperatures in an urban area are higher than they are in the surrounding rural areas. So if the rural area kind of represents what a quote, average or normal temperature would be, and if you have a higher temperature in the urban areas, that means that kind of a lot of the anthropogenic activities and buildings and things like that are increasing temperatures. So those, as you can imagine, are also affected by albedo as well, and that can be albedo of surfaces like pavements, but also buildings as well. So all of these things play together. And what's interesting, particularly in urban areas, surface albedo is really a significant portion of the area. And you can see some data here that was collected a few years ago on a few metropolitan areas. And when you combine roofs and pavements, it's well over half of the total surface area that's there. So talking about this is a big deal, and that's why there's been some studies at Lawrence Berkeley National Lab talking about that if we did some at a global scale, the change of urban surface albedo, it could really reduce radiative forcing equivalent to 44 gigatons of CO2 with a lot of significant energy savings as well. So because of that, people have proposed cool pavements as a potential mitigation mechanism for climate change and urban heat island. Cool pavements, they've talked about basically different things, but essentially, generally that means they're pavements that have a higher albedo. That is, that they reflect more of the sunlight rather than absorb it. And there's a couple different ways you can do that. You can do that with just by choosing different materials that naturally have a higher albedo, or as is shown on the right, you can also just coat darker albedo surfaces. So there are many different ways to do this. But because of that, there's no one single solution for a cool pavement. But it turns out that evaluating the impacts of pavement albedo is pretty complicated, actually, and there's a couple of reasons for this. One, if you make modifications to urban areas, it's actually possible that there are feedback mechanisms by which changes in those urban areas can actually have broader impacts on the regional climate. Two, as we mentioned, changing the energy balance for the Earth is what's known as a radiative forcing, and that's radiative forcing is literally just anything that affects that energy balance. So it's possible when you change the albedo of pavements, you are affecting that energy balance through a radiative forcing. The other thing is that pavements also affect the energy demand of buildings in urban areas, and they do this by a couple different mechanisms. One is essentially the incident radiation, that is the radiation that reflects off of that horizontal surface, then it can go into buildings and thereby affect the amount of energy that they need to do heating or cooling. The other thing, though, is that because of that radiative forcing, the pavements affect the ambient temperature around the buildings as well, and that also affects their heating and cooling demand. And of course, those can then have their own impacts on climate change, either through the electrical grid or through burning of natural gas for heating. Lastly, of course, whatever choices that we make for the pavements, those have life cycle impacts associated with the pavements as well. Environmental impacts associated with producing the materials, constructing them, using the pavements throughout their life, and then recovering the materials at end of life, right? And so all these factors, although it seems like you just say, make a cool pavement and everything's better, as you can see, it's not that simple because you have to look at all of these things together. The other thing that really makes this tricky is that context can vary significantly. The location in which a pavement is placed can have significant impact because, for example, depending on which latitude a pavement is placed at will significantly affect the amount of radiation that's absorbed or that hits the pavement. Of course, urban morphology or the shape of the buildings and the canyons all around it, that can vary drastically, even just from one city to the next and even within a city. Climates, the amount of temperature, the temperature and the amount of clouds affect how much pavements you see. Depending on how energy efficient the buildings are and what type of electricity grid can affect this as well. These are all really things that can vary significantly. So there's no real one single answer. But of course, that's what made this question interesting for us and why we've been going after it. So what I'm going to lay out here are some of the key research questions that we've had in our group. First, I mentioned the climate feedback. So we wanted to investigate whether there were climate feedback effects due to changes in pavement albedo. Two, how does the context affect the impacts of pavement albedo? And particularly, we're interested in kind of that comparison between the radiative forcing effect or the building energy demand, and that is one more significant than the other. And then lastly, how does the global warming potential due to albedo compare with other pavement life cycle global warming potentials? So, for example, one of the metrics we can use for life cycle environmental impacts of a pavement is global warming potential, and we can use that to look at the impact of producing the materials and then the use phase and things like that. So how does that albedo portion compare to some of those other portions? And then within that, so which climate change and urban heat island mitigation strategies then become the most promising? So kind of going back to what I mentioned here, all these different issues are essentially also outline the type of approach and analyses that we've done. So we have done some analyses of the regional climate in order to try to tackle that first question about whether there are climate feedback effects. Then we've also developed models to look at radiative forcing and building energy demand in urban locations to look at how the context affects the impacts of pavement albedo. And then we've used life cycle assessment models to be able to look at the global warming potential and how the albedo compares with other pavement life cycle global warming potentials. So what I'm going to do in this presentation is basically walk you through each of these. And I'm going to start here with this question about the regional climate. Now, to answer this question about climate feedbacks, we worked with some of our colleagues here at MIT who are climate scientists. And what we wanted to do is basically look at, if we make changes in urban areas, what impact will that have on regional climates? And so the way that they tackled that was by using this weather research and forecasting model, or WRF, and it actually couples a global climate model with regional climate models. And that's good for us because it allows us to look at, essentially what this is showing is the different scale of some of the grids that are used in the analyses. And actually, what's kind of neat about it is that depending on which regions that you're looking at, this is showing either 50-kilometer resolution or 10-kilometer. We can even go down to 2 and 1. And they use like a hybrid approach in order to look at some specific areas here. These little purple boxes right here are some of the urban regions. And what we did within this question is look at what happens if we increase urban albedos from 0.2, which is something that we would consider to be basically on average in those urban regions, if we increase that from 0.2 to 0.4 just in the urban regions, what impact would that have on the entire region? And they looked at it over 10 years. And the reason they did that is hopefully going to become pretty clear here. Here, what these individual boxes are showing are the results for the 10 years, and then this one is showing 5-year averaging and then 10-year averaging, okay? And what's being plotted here is the change in surface temperature between basically the control and then the analysis where we have 0.4 albedo in the urban areas. And the legend is down here, and what you can see is that basically like a cooler color actually represents cooling. That is that due to the albedo, you would get cooling, whereas a warmer color represents increase in temperature. So what one would expect is that in the urban areas, we would get cooling, but what's interesting here, depending on what's happening in the year, and these specific years were 2000 to 2009. And so this actually incorporates what the weather was like in those years. Some years you have El Nino, some you have El Nina, and those can really affect climate patterns. What's interesting is that in some years you actually get some of these feedback loops where you actually have increases because of all these changes in the urban areas, whereas some years you get significant cooling, and it can happen all over. So the year-to-year results are highly variable, and choosing one particular year as a consequence can it can really affect your results. But what's interesting, when you go to 5-year and 10-year, you see a lot of those feedback effects really dampening out. But what we can also look at is what's the temperature change in the urban areas. And what we see here is that basically if we just look at 1 year of data, so this is plotting like the variation across all 10 of those years, you can see a pretty significant variation, although they do show cooling in all of those urban areas. Whereas the more years that you average out the data, the narrower the band becomes. So I think the key thing for us is that if you are going to look at some of these different climate scenarios, that you look at least 5 years of data in order to kind of average out what could happen with the climate in any given year. All right, so coming back to our research question, are there climate feedback effects due to changes in pavement albedo in the urban areas? I mean, at least the short answer for the years that we looked at is no, but you have to look at that multiple years of climate simulations. the other thing that we confirmed is, what we would expect from the physics, right? The urban areas are cooler on average, and what we saw, it was about a degrees Celsius. So. All right, moving on now to this second question, where we're going to look at how does context affect the impacts of pavement albedo. And this is going to be now more about radiative forcing and urban building energy demand. And what's interesting here is that basically, I mentioned already we have this radiative forcing mechanism and then the building energy consumption. If we increase pavement albedo, what happens, right? What happens for radiative forcing, you get a negative radiative forcing, which leads to cooling benefits. But actually, if you increase the pavement albedo, you can get increased cooling due to incident radiation and reduced heating, whereas because of the ambient temperature, you get the opposite effect, right? You get reduced cooling and increased heating. So the bottom line is that we got all these different things going on, so it's hard to know without running the numbers what the net effect is going to be. And as I mentioned before, the context really matters because it depends on location, climate, urban geometry, building properties, the energy grid, and all kinds of those things. So what we did is basically we calculated the net effects of this radiative forcing and building energy demand, and we used two different approaches. For the radiative forcing, we developed a radiative forcing model, and it's an analytical model, and it accounts for many different things that are going to be location specific, like what's the radiation intensity for a specific location, and that's due to the solar zenith angle and the amount of cloudiness that we get there. And then, as you'll see, we've done then a case study of 14 representative locations. Whereas when it comes to building energy demand, what we had to do is basically develop a model that would account for the fact that there can be many, many different urban morphologies or, building densities, building scales, and things like that. And so we were still able to also, though, make it context-specific to a particular climate using some models that account for that, both the microclimate and the urban morphology. And then I'll show you a case study of Boston using that data. So once again, what we're trying to do is look at both of these things together and see what their relative effects are. And what I'm going to do first is tell you about that radiative forcing model. And once again, this kind of involves a lot of climate science and chemistry and things like that, so I won't go too much into the details. But as I mentioned, essentially what it is it's a model that accounts for that solar intensity, the amount of cloud transmittance, and solar angle. And actually what's great is that we get location-specific data from the WRF climate simulation. So that's how we're able to use that data in these models to look at the impacts of radiative forcing. We also can incorporate urban transmittance to account for shading effects in urban areas. If there are particular locations where we expect a lot of shading, then that's accounted for. And then we also account for the fact that there'll be a change of pavement albedo that will decay linearly over time. All right, one of the ways that we wanted to apply this model is by looking at what is the context of a bunch of these different climates. And what's interesting is that, as we mentioned, depending on the different contexts, we have this map right here is showing one of the ways that ASHRAE organizes different climates. So climate zone 1 is very hot and humid, and also has and that's predominantly, basically Miami has that by itself, whereas climate zone 2 has a hot and humid region, but also a hot and dry region, and climate zone 3 has warm, humid, warm, dry, et cetera, et cetera. So what we did is we picked representative cities in a bunch of these different climate zones, 14 cities to be specific that are listed here, and then wanted to look at impacts of changing pavement albedo via radiative forcing. And so because this is looking just at radiative forcing, this part right here doesn't account for BED. And what's interesting is that, as you'll see right here, this is showing some of the results, and this is showing the global warming potential savings from radiative forcing due to a 0.01 increase in pavement albedo per meter squared over 50 years, okay? And so we just choose the 0.01 just as kind of like a normalization, right? Just to say this is a linear effect, so if you're doing 0.2, you just multiply this by 20 to get the absolute number, okay? These green bars here are showing the range of GWP savings depending on a couple different model assumptions. And the cities down here are arranged from basically, you know, by the different climate zones. So Miami was the furthest one, South Climate Zone 1, going all the way up to Duluth, which was this Climate Zone 7. And lucky for them, very cold. But what you can see, there's a little bit of a decrease as you get further north. But what's more interesting, what I'm plotting here on this axis with these red triangles is the amount of cloud transmittance. So depending, the climate there affects the cloud transmittance a lot. And what's interesting, so even places where, you know, perhaps they are further north or something, like, you know, Denver here, if it has a high cloud transmittance, that also increases the amount of savings they get from radiative forcing, right? So no surprise, a place like Seattle has low cloud transmittance, and that also affects the amount of radiative forcing that it can achieve, right? So there's a big correlation there then with that amount of cloud transmittance. Just to kind of get a sense of how significant this is, we did an analysis of all the pavements in the U.S., so urban and rural roads across the U.S. You know, what if we did a 0.2 albedo increase? And this could be accomplished, you know, however, like I mentioned before, using materials, coatings, whatever. And so obviously it's pie in the sky, but it's just to kind of give us a sense of how big of an issue this is. And what this is showing is by state, basically, what the amount of global warming potential savings we could get in kilotons of CO2 equivalent per year, okay? So there's a couple of factors wrapped up in here. You know, one obviously has to do with its location, but the other thing that it has to do with is basically you know, how much traffic and how many roads they have, right? So Texas, which is far south and has a lot of roads, ends up having the most GWP savings. And just doing that 0.2 change to all the roads, it's equivalent to removing 756,000 or so passenger vehicles per year from Texas roads, or about 9% of the total traffic. If we look at the whole U.S., the savings are, you know, almost 10 million, or about, it's removing 10 million passenger vehicles, or roughly about 8%. So it has a lot of potential. You know, obviously it would take quite a bit to actually achieve that, but just to kind of give you an order of magnitude, it's significant. All right, so that's the radiative forcing and the model and some of the ways that it can be applied. Now what I want to do is talk a bit more about the building energy demand, which is quite different. And the real challenge here with the building energy demand is we're talking about cities, and those are complicated places. But what we wanted to do was to be able to estimate the albedo-induced building energy demand at urban scale for any given context. And there's a couple different ways in which people have tried to do this, and basically there's a top-down approach and a bottom-up approach. You know, a top-down approach would be basically where you look at very aggregated data from across the city, whereas bottom-up means you try to look at individual buildings and then scale it up, right? The top-down is challenging because it's hard to really be able to look at, you know, specific neighborhoods and how context changes across some of those different neighborhoods, whereas the bottom-up is really computationally prohibited. And so what we did is we used like a hybrid or a combined approach of both of these. And I'll tell you about it, but a big way that we ended up organizing this is using an approach that was developed by some researchers where they call local climate zones, or LCZs for urban temperature studies. And it's meant to be exactly like this. So they basically developed 10 different archetypes of local climate zones, ranging from LCZ1 to LCZ10. And you can see the LCZ1 is compact high-rise. whereas LCZ2 is compact mid-rise, compact low-rise, moving basically, they range with like different amounts of density, different building heights. So, and they have a bunch of data that basically says, here are factors related to the morphology of this region, and that allows you to basically characterize which type of local climate zone you're in. And as you can imagine, the type of local climate zone you're in is going to really affect the BED that's experienced due to a change in albedo. So the approach that we used was, basically ended up using a whole bunch of different tools, actually. And it involved a couple different steps. Essentially what we had to do is kind of be a bit generic or about different types of neighborhoods, and then you basically run those a whole bunch of times in order to get data on energy consumption, and then try and match that with actual data on cities. So the first thing we do is basically use some tools. Rhinoceros is one that's basically like a CAD tool that allows you to draw different configurations, and Grasshopper is a tool that allows you to, it's a plug-in to that that allows you to basically do a whole bunch of parametric analyses. And so what we did is basically use that to get a whole bunch of those for many different local climate zones. And actually, this is basically, what the type of analyses that you can do, is change the different geometry of the buildings and how far apart they are, and going through all of those different ranges is what allows you to basically develop these models, okay? Then what we do is basically, once we analyze all those, we need to quantify energy consumption. And we do that using a couple other plugins for Rhino, which are called Honeybee and Ladybug, and they clearly really like the insect theme with their plugins. But essentially, the energy analyses rely on Energy Plus from the U.S. Department of Energy. And then in order to look at the effects related to the ambient temperature, we used a tool that's actually generated here out of MIT called Urban Weather Generator, which allows us to modify the climate files that are used in those energy analyses to account for that. And so what we calculate is basically then a change in energy due to the radiation effects that come from energy, bouncing around within those canyons, and a change in energy consumption due to temperature effects, and a change basically, by changing the albedo, okay? And then we do a design of experience to basically analyze a whole bunch of scenarios, but in basically an efficient and smart way for a range of different local climate zones. What we do then is basically do some statistical analyses on those to understand what are the attributes of those all those different analyses that we ran, and then we can use that to develop these statistical meta models. So then we can basically say, we have a lot of confidence in the results that we can quantify that change in energy, including both radiation and ambient temperature, for a change in albedo, okay? So we get this statistical model that allows us to do these energy calculations then for a particular climate, but then for a range of different urban morphologies. What we can then do is basically take GIS data for a specific region and apply that meta model to the GIS data so that for like a specific neighborhood, we can then understand what happens when you change the albedo in that specific neighborhood, okay? And so if we know what the morphological parameters are for that urban neighborhood, we can then calculate what's the change in energy due to a change in albedo. So. All right, so let me show you a case for Boston. I'm showing this here. It's a little bit to scale. MIT is not too far away over here in Cambridge, actually over here in Cambridge. That's the Charles River. So a lot of Boston goes south. There's a few harbor islands, but so this is the whole Boston neighborhood. And actually, so we were able to get data on buildings and pavements from either basically the State Department of Transportation, and then also but City of Boston, and a lot of that's available online. And then we use QGIS to analyze the GIS data, and Tableau to visualize it, but we get a whole bunch of data on roads and buildings, and a lot of times it's organized by these different census tracts. And the data that we get is building heights, building lengths, canyon aspect ratios, and building densities. So breaking it down by those local climate zones, what you can see, you may recall, climate zone 1 was the highly dense urban areas, and then basically getting down to climate zone 9 was where they were more lower and more spread out. So what you can see is that obviously Boston has its kind of like its urban core. This is the financial district where you have a lot of the tallest buildings, but then in the Back Bay and South Boston, you get some that are a bit more spread out, but then here's all the residential areas, right, where the buildings are pretty well spread out. So from an area standpoint, this high density, what we consider, to be deep urban canyons, is a very small fraction. Most of it is actually residential. Then what we can calculate is basically global warming potential savings from cooling and then also from heating. And basically, in this context, the orange actually means that it's a burden. There's an increased burden due to cooling. And as I mentioned, that makes sense, because as you're increasing the amount of radiation, then you actually get more heat that's going into the building due to the radiation in the summer, so that means you have to do more cooling, but of course that means in the heating, the blue means you get more of a benefit in the winter, right? So we have to, in Boston, we have to look at those relative amounts, and when we look at it in aggregate, we can see it's a pretty broad mixture as to whether it's a burden or a benefit, and this is just showing that building energy demand right here, okay? Now, what we have to add into that then is what's the radiative forcing and how does that compare with the building energy demand for cooling and heating. And the way these charts work is essentially, it's called a waterfall chart, and we end up starting at 0 here. So this is for the LcZ9 in the financial district of Boston where we had those really tall buildings. And we start at 0, and in that you actually get a relatively small radiative forcing benefit because there isn't, because the buildings are so tall, you don't get much of a benefit from changing the pavement albedo. And in fact, what you see, though, you do get a big burden due to cooling. You get some benefit due to heating, but then this is the number in net. So what that means is that we're looking at GWP savings here, so you actually have a net burden in that local climate zone. However, when we go out to all those residential areas, LcZ9, you see you get a big burden, or sorry, big benefit from the radiative forcing, a little bit of a burden for cooling, a little bit of a benefit for heating, but in net, it's a really big benefit, and it's mostly has to do with that radiative forcing, right? So this just gives you a sense of how, really you have to look at what that local climate zone is in a, in a census tract or in a neighborhood, and why you have to kind of run those numbers and compare it. What we see so far, though, is that in really dense areas, it usually looks like this, that the BED is going to be bigger than the radiative forcing, whereas the reverse is true in many of those other neighborhoods that we see in the cities. The interesting thing about using the GIS data is that we can actually do some pretty highly localized analyses. So before I was showing it kind of aggregated by census tract, but we can actually have the capability to go in to look at specific buildings. So this is actually in a particular neighborhood, and a lot of them, kind of the burdens or benefits that you see are aggregated, but in some places where you get a bunch of different heights of different buildings, this is showing some of those tall buildings, at least from an aerial view in the financial district, you can actually get a wide range of different results. So what we're still playing around with is trying to understand to what extent is it beneficial to aggregate versus to what extent can you do individual building analyses. So All right, so let's come back to our research question here. How does context affect the impacts of pavement albedo? What we see, at least in this case of Boston, for that location and Boston's climate, that for dense urban neighborhoods, the BED is larger than radiative forcing, primarily due to shading, and global warming potential is a net burden. Whereas in most other neighborhoods, the radiative forcing is larger than the building energy demand, and GWP is a net savings, right? So that can really, the strategies that you might use should really depend on which type of neighborhood that you're in. So our next step with that research is to evaluate other locations and climates. We've already got data from Phoenix and have started looking at that GIS data and doing similar analyses. And as you might expect, the burdens and benefits for heating and cooling there are quite different. So that'll be an interesting comparison as well. All right, last but not least, putting this in a life cycle assessment context, when it comes to just sustainable pavement design in general, there are questions about the pavement life cycle. You might be just looking, if I just am looking at, my objective is to make the greenest pavement I can, you might be wondering, should I use materials with recycled content or increase surface albedos? Maybe you have the opportunity to do both, but we are interested in those relative impacts. However, if you have a specific instance where you're looking at cool pavements, and that's really your primary objective, you might be interested, what are the life cycle environmental impacts of cool pavements? So to be able to answer that, we've applied a pavement life cycle assessment model that we have. And it includes the environmental impacts of extracting and transporting materials to a construction site, doing construction, looking at maintenance throughout its life, and then end of life as well. But of course, in the use phase, we have a couple different elements here. We have impacts of the reflectivity due to lighting. So the higher reflectivity of a surface, the lower the lighting burden. Carbonation for some materials are able to absorb carbon dioxide. And we have these albedo effects we've just been talking about. We also quantify excess fuel consumption of the vehicles driving on the pavements, either due to the roughness of the pavements or due to the stiffness of the pavements, the amount of deflection that they induce. And we've covered that in some previous webinars. But basically, this excess fuel consumption, there's a certain amount of fuel that's required to move the vehicle forward. This is an additional amount beyond that. Associated with the condition of the pavement and the design of the pavement. So obviously what we've been talking about here, what we can do with that radiative forcing and building energy demand analysis, we can combine those together to use in here in that global warming potential and then compare it with these other instances. So we just started doing some of this work, and one of the key things about these pavement scenarios, you have to ask a question about what's the goal of the analysis? And like in particular, is climate change or urban heat island mitigation explicitly part of the pavement design goal? And the reason I mention that is because, if you're looking at a pavement where, it's just a regular pavement, it's just going to be designed to carry the loads of that pavement, but you want to look at the secondary impacts of that, that's one thing. But you may be saying, I only want to be able to use pavements that are going to mitigate these effects, particularly of urban heat island. So we have right now here a couple different scenarios. PCC is Portland cement concrete and AC is asphalt concrete. And we had a pavement designer come up with pavement designs and then calculate deterioration throughout their life, and then also use some different rehabilitation strategies. And so I won't get into those too much, but what I will bring your attention to is what are our assumptions for the aged albedo values here, right? So aged albedo means this is always a tricky thing because the albedo of pavements evolve over their life, right? And what we're looking at here is like a 30-year design life and a 50-year analysis period. So, of course, they won't be static. And we're not at a point yet where we're dynamically accounting for what that albedo is over time, primarily because I think we benefit from some better data in that space. But the albedo here, what we've chosen are some values that have been published by University of California Pavement Research Center and Lawrence Berkeley National Lab. So it kind of, and they publish some ranges, so we've chosen some middle ones. But for concrete, then, an aged albedo value of 0.25. It's also possible to create concrete pavements with white cement, and actually those start out with the albedo of 0.7 or 0.8, but then they age down to 0.5. Asphalt's aged albedo, it's within a range, but generally values around 0.1. But as I showed earlier, there are coatings that can be applied, and once again, I think they start out with a higher reflectivity, but they end up aging down into this range of 0.2 to 0.3. But what's interesting, I think that there are opportunities to kind of do a similar thing where you use kind of more a higher albedo scenario. So this value right here is not something that's been published, but what we're interested in is basically through the use of coatings, can you also achieve some of those different levels. So once again, there's a bunch of engineering that I'm not going to go into that went into what's the construction, what's the rehabilitation, and then some other studies measuring albedo here. Now, when we look at here, this is showing for some of those different scenarios. There's a couple things going on here. Once again, this is showing the pavement life cycle global warming potential, basically in megagrams of CO2 or tons per mile of pavement. And the red is the construction impacts. Yellow is maintenance and rehabilitation. Blue is the albedo component. Basically, these ones right here are the impacts of the use phase, right? And then a little bit at end of life right here. So I think that the key thing to talk about is that there are very different impacts associated with initial construction and then that maintenance and rehabilitation. And then but what's interesting is that the albedo impacts are quite different. And what you might notice right away is that some of them are positive and some of them are negative. And that's because when we talk about a particular impacts in a life cycle perspective, we have to use a baseline. And what we've gone with is using the albedo impacts relative to the average of the Earth. And there are different ways you can do this, but as long as you choose the same baseline, you'll get the same relative results. And so that's why in these high albedo scenarios, obviously their albedo is higher than 0.3, and that's why they're negative. And that's also what this means. This lines right here for the negative ones, this is the net result, right? Because these are all positive, and then we take off that negative. That's the net result that we get for those. So the key conclusion you see here is that, obviously you're going to have higher initial impacts in the concrete, but then different impacts throughout the life cycle and due to maintenance and rehabilitation. But generally, the higher albedo that you get, the more benefits that you get from those. So there are a range of different options. This is for the LcZ9. Coming back to our research question, our preliminary results show that the comparison of the scenarios, it really, which one of these that you compare is going to depend on what's your goal. Like, these are just conventional pavements right here, so you could compare those, or you could compare basically the more higher albedo scenarios, right? But bottom line, the albedo, it really can be a significant portion of that pavement life cycle. So as I mentioned, that's kind of some of our preliminary work, and so what we're going to do is evaluate some more of the relative impacts of albedo for a range of different scenarios, depending on location, climate, the local climate zones, which materials you're using, are you using recycled content, which wasn't the case in any of those, what are your maintenance and rehabilitation strategies, and then also which albedos are you choosing. All right, so just to wrap this up, as I mentioned, we've kind of gone through this journey of looking at regional climate issues, the comparison of context for radiative forcing and building energy demand, and then looking at that overall life cycle. And I hope you've come to appreciate why I made that first statement about this being complicated. But I think we are able to draw some conclusions already, and that is that, increasing the pavement albedo, it does have significant potential to mitigate impacts of climate change and urban heat island effects. And obviously, those are going to be context specific, and so we have to look at specific instances for when we apply those. as I mentioned with the climate simulation models, it's really important to run those for multiple years to extract out the effects of any particular year, which may deviate from more of a, we're trying to figure out what's the signal from the noise there. At the national level, particularly outside of urban areas, there's significant opportunity for radiative forcing benefits. When it comes to BED impacts, they really depend on the urban morphology, and they do not favor, and they do favor less dense neighborhoods. They don't particularly favor more dense urban areas. Radiative forcing is more significant, though, in most of the neighborhoods, at least that we saw in Boston. So, when it comes to life cycle environmental impacts, the albedo can be a significant portion of the pavement life cycle, but it really is context sensitive. So with that, I'm glad here's our contact information. We have our website where you can find more information, and that's how you can send us an email, and I'll be glad to answer any questions.
Great, thanks. We've got a couple that have come in already, but just a reminder, if you'd like to ask a question, there's a Q&A box in the upper right-hand corner of the screen, folks. And Jeremy, your screen seems to have closed. Can you bring up the presentation?
I did that because I think if you want me to be able, it looks like I can't do the Q&A and also share my screen.
Gotcha.
So
why don't I read the questions?
Yeah, that sounds good. Then I'll go back to,
Perfect, thank you. So the first question is in regards to, it was asked at slide 40.
Yep.
And the question is there an average, there is an average of 0.1 degree of centigrade change temperature due to a 0.01 change in surface albedo. How does this change in temperature alter in the summer and winter? So is there a climate impact? Temperature. Seasonal.
So like what are some of the temperature impacts of these? And I should have mentioned that basically when you use these higher albedo scenarios, you pretty much always get ambient air temperature cooling. And it depends on the amount of pavement that you're talking about, and a whole bunch of different factors. But just for like the areas that we're talking about, changing it in, say, an urban context, you're talking about like a fraction of a degree Celsius, anywhere from 0.1 to 0.5 are some of the ranges that we've seen in terms of temperature changes.
Thank you. On slide 41, it says you have a baseline for EFC, DEFL, and albedo, therefore relative change in environmental impacts. But for other life cycle phases, they're basically in absolute values. Are the base case in AC and PCC the same?
The short answer is yes. They are their absolute values in that, like with construction, we're just looking at impacts of making the materials and doing the construction. So those are kind of more absolute values. Like I said, in the albedo, it always ends up being relative. The excess fuel consumptions actually generally have a baseline as well, like particularly when it comes to roughness. When it comes to that excess fuel consumption, what we do is we define a baseline of essentially a new pavement. And then the excess fuel consumption is how does the roughness evolve over time for that. So, but those do have the same baselines for asphalt and concrete, just like we used the same relative baselines on the albedo.
Great. The next question is, when uncertainty is figured into this analysis, how does it reflect in the results?
Yeah, that's a really good question, and I should have included that in our next steps as well. Our life cycle assessment model is probabilistic, and that's one of the things we really need to explore. And so the short answer is how we've been doing that implicitly is basically by looking at different scenarios. But we can account for uncertainty and what the actual albedo is, and the roughness, and so that's definitely next on our list as well.
Great. Specific to slide 32, what is the time scale?
32, let's see. So, sorry, and I should have mentioned this. It's 50 years.
Great, thank you. Lots of questions coming in. Let me just scroll up for a second.
Good, that's fine. I'm ready for them. So.
On the earlier side for climate by year, I don't understand how how in some years near the center part of the country, higher albedo is not helpful. So
I think I know which one it is. Let me go to it. I think it's this one right here. This is it. What's kind of crazy about it, these ones basically, it's hard for us to predict exactly what that climate feedback would be, because essentially what we're doing, remember, we just changed the albedo in the urban areas, right? And so like these temperatures right here, so even in these years right here where you have this, in the urban areas, they're still cooling. But because what you've done is you've changed some of the ambient temperatures in those regions, and you've affected the radiative balance as well, depending on what is happening with the climate in that year. In terms, maybe just in some years there's a lot more movement within the climate, and like I said, I'm not a climate scientist, so I'm not exactly sure. But you know, that's what can happen. You can get some of that feedback, and so it's just part of the complicated mechanisms of what happens in our climate, and that's why it's hard to predict that. But as I said, the primary objective with this is kind of looking at the signal. What's the signal and what's the noise, right? And the problem is that any given year you can get a lot of noise in terms of what's happening in the climate. But what we want to do is say, in the long term, what kind of benefits are we gonna have?
Thank you. Next question is the GWP from the UHI, so that's global warming potential from the urban heat highland part of an LCA, and say the construction part are different from each other in terms of localization. The UHI GWP is a global effect, while that from construction is local. Any thoughts on directly comparing these two?
No. I mean, global warming potential is a global number. So like even when you do construction locally, you emit the carbon dioxide up into the air. That's a global effect. So I think maybe the slightly different question is basically, and that's why actually we presented some of this work to other people, and they say, well, if I'm interested in urban heat island, what I really care about is temperatures. Right, and so that's why I think kind of going back to some of these scenarios and which ones that you want to look at, you could get some people who basically say, you know, I'm worried more about deaths right now due to urban heat island that's happening right now than, you know, maybe deaths in the future associated with climate change. And that's a difficult question, but it might be a trade-off that you'd be willing to make. And I think ideally you're able to do something that can help mitigate urban heat island and mitigate climate change. But that's kind of, I think, maybe the bigger deal with the local versus global. Urban heat island, a lot of times they're interested in temperatures, whereas any construction or whatever, no matter where it happens, that still is a global metric. So.
Great. For tropical countries such as Costa Rica, where we don't have any need for heating in the winter, the net impact of increasing albedo will be negative at the end of the analysis? Will be?
It actually, not necessarily. It really depends on what's the morphology of the buildings in a particular region. And what I mean by that is that basically, even though you don't have any heating, there could be a net burden due to having the reflection of the radiation from the pavements go into the building. And so that could happen there, but as I mentioned, you have to compare that with the radiative forcing benefits. And so that's kind of the thing that you'd have to analyze. But taking off heating is one thing, and as I said, we're analyzing Phoenix right now, and that's certainly some of what we see. You know, in really dense urban areas, you can definitely get a net burden due to building energy demand, but you have to look at how that's offset by the radiative forcing.
Great. On slide 41, the next slide, on slide 41, it appears that PC rehab GWP equals the initial cost of rehab GWP. What is the assumption?
noticed that myself, and I think that's something that we got to check, because the assumption here is full depth repair, and actually I know that basically what the pavement engineer told us is all that means is just like, it was like 0.4% of a slab replacement in diamond grinding. So I think, like I said, that's kind of goes along with the preliminary results. I think that is too high. So, but I got to check that. So it's a really good point.
Great. And the last question we have today, the issue of surface glare, and I should say, if there are any others, we just have a little bit of time left, but
sure.
We can certainly follow up with folks after the fact. So if you have another question and want to enter it, we can get in touch separately. But the last one that I have on the list today is the issue of surface glare behavior falls outside the science you've presented, but may impose inherent limits on what levels of higher albedo would be desirable for urban pavements. Do you believe that glare might become a problem with higher albedos?
I think it certainly could be. Yeah, there's no question. It's something that we have to look at. I think that this is what I think really presents an opportunity for us to look at how we design cool pavements for this mitigation. Like I mentioned, you know, the white cement concrete pavements, they start out with an albedo of 0.7 to 0.8, but then they age to 0.5. So I think there's an opportunity there to basically say, how can we just get it to kind of stay at that? And it may not be possible, but I think you're absolutely right that glare is a big deal. I mean, certainly people drive on pavements that are covered with snow at certain times, and you have to deal with that. But there's no question it should be a factor that should be considered in the design of these pavements. So.
Great, thank you very much. And thanks everyone for attending today. Again, we appreciate you being here, and we appreciate you attending these webinars. We have another session scheduled for next month, March 13th.